Okay, so I want to just make sort of a observation. So I get my ESPN updates so that I can be informed enough about football to engage everyone in social conversation. But something struck me about the stats for the next two games. And so if you just look at it, right, so if we pick Army, right, and we take a look at the records, 2-0 and 1-1, right, and we look at the, no, I don't want Cincinnati, and we look at the points per game, right, and we look at total yards and yards allowed, and we do the same thing with UNLV, right? On paper, both of these teams can be considered significantly better in terms of these stats, right? So does anyone honestly believe? Apparently Vegas doesn't, right? Because we've got almost a 31-point spread against Army, right? So the collective wisdom of football, people who bet on football, is strongly in the favor of the Buckeyes, right? So does anyone actually believe these stats? Probably not, right? But they're real. So I brought this up just as a cautionary tale of both reading things, scientific papers, and coming to conclusions from your own experiments, that it's not just a single measurement that you have to consider, right? It really is your overall scientific knowledge, right? Engineering intuition, familiarity with the material as it is, that can lead you to the right conclusion. And it's very easy to go to the wrong conclusion from a limited series of observations. A big one, so I can bring this back to aluminum, right? Believe it or not, I can. So from mechanical behavior, right? Do you expect materials with high stacking faults or low stacking faults to twin more readily? Mechanical twinning, deformation twinning. High stacking fault to twin more readily? Low stacking fault to twin more readily, right? Is aluminum a high stacking fault or low stacking fault material? High. It's high stacking fault, right? We never see deformation twins. Oh, okay, so I need to swap displays. Where's my pointer? Why my wife is calling me during lecture, I don't know. So aluminum is a high stacking fault, right? We never see deformation twins in bulk aluminum, right? Now, there was somebody who was an expert in mechanical behavior, very well-known scientist, who did a lot of TEM observations of aluminum. And in the thin foil, aluminum twins readily, right? Completely different situation than in the bulk. And they developed a whole theory of dynamic recrystallization by twinning in aluminum alloys, right? It was very sound based on the observations, but completely out of the ballpark based on a more holistic understanding of the behavior of the deformation behavior of FCC metals, right? And it's very easy to fall into those sorts of traps, right? That's sort of wrong thinking without having enough of a bigger picture. Okay, so that's enough of my cautionary tale. So we started on Wednesday looking at some of the microstructural features that control the properties of aluminum alloys. And the first microstructural feature was the presence of coarse intermetallic compounds. And for the purposes of the upcoming discussion, we'll consider these in the range of 0.5 micron to 10 microns. They're going to form during solidification and processing. They tend to align in these stringers as a result of mechanical fibering. Right? During deformation, if we have particles at grain boundaries and we have equiax grains that we then pancake out, right? We end up with long stringers of these particles, and we can generally break them into two classes: soluble, which don't have a clear solvus on our phase diagram, and we have to take them up to the liquid to dissolve them, and soluble, which will dissolve back into the matrix at elevated temperatures in the solid state. Right, so that's the first microstructure feature that we want to consider. Smaller submicron dispersions of intermetallics, right? And we're going to sort of lump this in the range from 50 nanometers to 0.5 micron, right? And these are the particles that are going to help us a lot with grain size, right? These are going to tend to retard recrystallization of grain growth. Okay. Then fine precipitates. These are the nanometer scale particles that we spent a lot of time talking about in the age hardening section, and this is the basis of our high strength in age hardenable alloys. The other things that we want to consider is grain size and shape, the dislocation substructure that develops during any working or mechanical processing operations, right? And for the rest of today, we want to consider the effect of these features on the properties of our alloys. And we're going to keep everything separate. We're going to talk about the alloys that respond to heat treatment, otherwise age-hardening alloys, and then the non-heat treatable alloys, where we rely on all the other strengthening mechanisms we talked about this week: cold work, solute solution strengthening, grain boundary size. Okay, so what about coarse intermetallics, right? The main effects is that they really don't affect the yield strength very much, right? They don't affect the ultimate tensile strength very much, but they do have a very marked effect on the ductility, right? These intermetallics are very brittle; they'll crack. Right now, we have a void in our material, right? Remember our working of the material, right? We tend to align the grains and get these stringer formations, right? And that gives us a strong anisotropy in the mechanical properties. So that means whenever we report the properties of a cold worked alloy, we generally have to think about it in three directions, right? The first one is along the fiber length, the transverse direction, and then the short transverse direction, which is normal, right? So if we think about rolling, right, along the fiber length is the rolling direction, right? Because we're taking these grains and we're smashing them out. So these aren't just necessarily a stringer, right? These are sort of plate-like regions where you're have a whole bunch of particles embedded, right? And so it makes sense if we think about pulling along the rolling direction, pulling transverse to the rolling direction, and pulling along the normal direction. The normal direction is what is called short transverse here. And our properties tend to be the greatest in the longitudinal direction and least in the short transverse due to the fact that we're now pulling in an orthogonal direction to these stringers of intermetallics, right? Remember that force has to be the same through the thickness, right? If I'm pulling normal, right, I'm hitting a much larger planes that have a much larger cross-sectional area than intermetallics, right? And so if we look at these, if we consider two alloys, a 7000 series and a 2000 series, right? Our ratio of, and we measure it in the three directions, our ratio of the strengths isn't all that anisotropic. You maybe get a couple percent reduction in strength along the difference between the short transverse and the rolling direction. But if we take a look at elongation or ductility, we have a huge difference, right? We lose ductility by more than a factor of 3 in some alloys, a factor of 2 in most alloys, right? So we can't ever think of metals in general, or aluminum in particular here for this case, as being homogeneous and uniform as a result of mechanical processing, right? We can homogenize a lot of this by thermal processing, right? But whenever we deform something, we introduce large amounts of anisotropy, right? Yeah.
What do you mean by large amounts of anisotropy?
Directions in our sheet, right? So if we're making sheet metal, right?
Oh,
okay. Our ductility, if we do a tensile test of a sample that's cut out parallel to the rolling direction versus transverse. Well, sometimes you can, right? So if we have an aged alloy, right, we can form it, but then we would have to solution heat treatment, quench, and age again, right? That we can do, but there are some systems where we're tied, right? We're really hindered because treatment like that could also grow, depending on what the system is. In these two systems will be fine, but in other ones the subsequent thermal processing will grow our grains to a size that we may not be able to have, or we may lose an important texture, right? So for an iron, for transformer steels, right, you've got a big difference in magnetic susceptibility according to different crystallographic directions. So you try and do grain boundary engineering to get sheet metal for transformer cores that are where the high susceptibility directions are aligned, right? And if you do subsequent thermal processing, you destroy that, right? But then you lose, right? It's always a balance between the properties. And unfortunately, most of the time, it's a balance, a trade-off between what you want, right? You want high strength, high ductility, high toughness. But strength and ductility and strength and toughness are usually inversely correlated with each other. Okay, so the other property that we want to consider is the effective grain size. And I had mentioned that the Hall-Petch coefficient for FCC metals is very low compared to BCC and HCP. Aluminum is particularly low, or 2 orders of magnitude less than good steel alloys for for Hall Petch effect, right? But where aluminum saves us is that we can get very small grain sizes, right? How can we get and retain the small grain sizes? We'll talk about that next, but it's the presence of those submicron scale precipitates that are going to retard grain growth by pinning, right? So we can get a huge range of grain sizes. So even though the slope of this line is very shallow, the fact that we can get 3 orders of magnitude on grain size means that we can get a factor of 3 increase in strength due to grain boundary engineering. Right? And this is all the stuff that sort of goes into the design, right? The chemistry is just the first part, right? You select your alloy, but then you got to think about what am I going to do with it to get the properties that I want, right? So it's not just which alloy am I going to pick. Okay, so recovery and recrystallization. So very pure aluminum alloys are going to statically recrystallize actually at room temperature. So if you take 5/9 pure aluminum and you cold work it to 95% strain, you're going to completely destroy your grain structure, right? You'll have these huge pancake grains. Set it aside and come back a week later and you'll have beautiful, clean, equiax grains, right? So in pure aluminum, cold work is not an effective mechanism for raising the strength. So just as a refresher, what's the difference? I have recovery and recrystallization. Right? What's recovery?
Annihilation of dislocations.
Right, annihilation of dislocations, but you're not changing your crystallographic structure. Right? And recovery, both recovery and recrystallization happens in 2 forms, static and dynamic. So static recovery is recovery that happens under thermal processing, purely thermal processing. Dynamic recovery happens under mechanical loads. So as you're deforming it, you're driving dislocations that are going to interact with each other and annihilate, right? So in terms of dynamic recovery, we have thermal and athermal effects, but that's sort of a sidebar. Recrystallization, we also have static and dynamic recrystallization. Static recrystallization is we cold work and then we anneal, right? And our new grains grow to remove the dislocation content, right? And we can also have dynamic recrystallization. Aluminum does not dynamically recrystallize very easily, right? Why do you think not? Copper and nickel undergo extensive dynamic recrystallization when you're deforming them at temperature. Aluminum tends not to. What's the main difference? What's the important thing that seems to control so many properties? Stacking fault energy, right? Aluminum, because of the high stacking fault energy, very easy to cross-slip. So we have very high rates of dynamic recovery because dislocations can change slip planes, get around locks, right? And they can annihilate each other. Whereas in copper and nickel, other FCC metals, you can't do that. Remember when we talked about planar slip versus wavy slip during the very first section, right? Aluminum slip lines are crazy because the dislocations can move around obstacles. Right? So there was a question. Yeah.
Yeah. So because stacking fault energy is so high and dynamic recovery occurs generally, you don't then how is it that you're able to still see some dislocation rates or somewhat cellular structure? So very diffuse.
Well, you still see it because you're not eliminating everything, okay. Right? I mean, the fraction of dislocations that you remove during recovery is fairly small compared to the total dislocation content. Remember, you're still deforming. You're in dynamic recovery. You're still deforming plastically, so you're still generating, right? Dynamic recovery saturates when the amount of dislocations you're generating and the amount that you're removing balance, right? In static, you remove more, right? And you tend to polygonalize your grains, right? But you still don't completely destroy your substructure. You still have significant amount in there. Okay, so as we decrease the purity of our aluminum, we retard, and this is still impure aluminum. This isn't necessarily in the alloy. We retard recovery and recrystallization due to solute drag effects. Okay, so here's a term that when I put the notes together, I assumed everyone was going to be familiar with. Right? What on earth do I mean by solute drag? Okay, yeah, right? Yeah, except here we're talking about grain boundary, right? So we have solute atoms that are going to segregate preferentially to the grain boundary because that's a low energy configuration, right? So now if I have can maintain a low energy by keeping solute atoms preferentially at the grain boundary, and I go to move my grain boundary by thermal force, what's going to happen? Right? I'm going from a lower energy locally to a higher energy. So the way to maintain the low energy is to only move my interface at the same speed that my solute can diffuse. I'm dragging my solute along with the grain boundary. Right? That's the physical simple picture, right? If this were the phase transformation and kinetics class, right? We talk about that in quite a bit more effect, right? But notice this is a problem with the things we can't remove: aluminum, manganese, and silicon, right? Right. Those are the ones that tend to form these insoluble particles and stuff we can't get out of our alloy by processing. And so this is the big take-home message here, right? Very small variations in the purity can result in very significant differences in the microstructure and the property and the ultimate performance of aluminum alloys, even ones that go through the same processing steps. Okay. So the next one on the list was toughness. Okay. So toughness is a huge one, right? Because we use metals because we can dissipate a large amount of energy through plastic deformation. It means we fail things in a controlled manner. If our toughness gets low and we move from a ductile fracture to a brittle regime, then all of a sudden we're in trouble, right? Remember when we first started talking about aluminum, I said, what are the reasons that we use aluminum? And I specifically pointed out that there isn't a bulk phase change in the temperatures that we're interested in. So that means we don't need to worry about a ductile to brittle transition, right? However, if we do something with our processing that reduces our toughness enough, that benefit goes away, right? And tensile strength happens to be inversely proportional to toughness, right? And just as a quick reminder, tensile strength is resistance to failure by mechanical overload, right? Toughness really here, the fracture toughness, is the energy under the stress strain curve, right? And in the presence of flaws or other defects, can drastically reduce the amount of energy that we absorb or dissipate. So in aluminum alloys, we have ductile failure, right? Which means that we sort of get voids that nucleate and coalesce, and you get these fibrils, right? Okay. So now if we have a series of large intermetallics, right, we can get, notice that the crack path follows the largest defects, largest particles in our structure here, right? So the distribution of particles is of prime importance, right? So if we tend to have large linear arrays of large brittle intermetallics, that would be bad, right? Right. What naturally happens when we roll our material? Right? We get just that, large linear arrays of brittle intermetallics. Right? So particles can cleave depending on the surface energy. We can have decohesion. Right? This gives us very large local strain concentrations, which can then accelerate the void coalescence. Right? And depending on the alloy, we can also zip along grain boundaries, right? Especially in alloys that are subject to stress corrosion cracking, like aluminum mag, right? If we have a large amount of grain boundary, a brittle grain boundary beta, especially in a hydrogen environment, it becomes even more brittle, right? Then we have a crack that just can zip along the intermetallic that's on the grain boundary, right? Without much resistance. Okay, so the first thing we want to do is try and reduce the level of iron and silicon. So if we take a look up here, so up here, this here is this fracture toughness of the same alloy, but with greater than 1% iron and silicon impurities, and here less than 0.5%. Right, so you can see a clear difference in the performance of these based on small concentrations, changes in the concentration of iron and silicon. Right. So silicon, we'll talk about this in the next lecture. We use alloys with a huge amount of silicon in them, right? But those are mostly casting alloys, right? And the silicon gives us really good flow properties, right? So they're in a different sort of group than in the wrought alloys, and they tend to be used in different applications. Right? Cast aluminum versus wrought aluminum. Okay, submicron particles, as I said, are before, right? These are the ones that suppress recrystallization and inhibit grain growth by pinning. Right? Remember, the mechanism of that is the particles are on the grain boundary, and they have a lower surface energy than the grain boundary surface energy. So the boundary wants to stay right there, because now I've got aluminum and aluminum touching this low energy surface. Instead, if I move the particle off, now I have a higher energy grain boundary interface. Okay. The good about this is, again, we suppress recrystallization, and then these fine unrecrystallized grains, when they do fail, they will favor this intragranular as opposed to intergranular failure mode, right? So the cracks will cut across grains rather than going along the grain boundary, right? And so we can see here again, this is fracture toughness, right? And we can see here that the fine elongated unrecrystallized grain. So in so elongated pancake from deformation, right? We have a higher plane strain fracture toughness. If we recrystallize it, we lose a little bit, and then if we grow the grains out large, we greatly reduce that. fine precipitates from aging, this is what we spent a lot of time talking about, right? We get very high strengths, strengthening effects, but we can also increase some toughness because the we have a much more tortuous path. We don't have a large things that can break and cause decohesion. Okay, so that's fracture. Fatigue is sort of another story, right? So fracture is, we just pull it till it breaks. Fatigue is we cycle back and forth. And in fatigue, we haven't made the big gains that we have in other alloy systems, right? So this chart down here, so this is the tensile strength of an alloy. This is the endurance limit, right? What's the endurance limit? Right? It's the amount of cyclic stress load that we can put on something and that it will survive indefinitely, right? That the average piece, right? That we don't measure any actual fatigue failures on, right? So if our fatigue load is under the endurance limit, we don't need to worry about its eventual fracture. But notice these lines. So this is, which one's which? Okay. So the non-heat treatable are these open circles, and the aged are the X's. But notice that this line curves, right? Meaning that we have a hard time increasing both strength and fatigue life. So the higher our strength goes up, the smaller the ratio between fatigue life and strength becomes. And now compare that to steels, right? This has a much higher slope. Where are we here? So we have a much higher slope for certain types of steel alloys. So in those cases, we can retain both the fatigue life and the tensile strength. Okay, so what makes fatigue different than fracture? Well, the cracks still nucleated at stress concentrations tend to be from the surface or other our internal voids, right? I should say fatigue cracks initiate at free surfaces, whether that's an internal free surface or an external free surface. It really doesn't matter much. Notches, corrosion pits, coarse slip bands. What's a slip band? Anyone familiar with the term? Right. It's different than a slip trace. A slip trace is just where things deform. A slip band is a region where the strain has been localized, so that as we go back and forth, we're sort of shearing back and forth on the same planes because we've gotten some sort of softening mechanism in there. Such as we had a fine degree of, we had a nice fine strengthening precipitates, but then we sheared them sufficiently that we reduced the cross-sectional area. Now they're not as effective strengtheners, right? And once a plane weakens a little bit, then we're going to keep going back and forth on the same thing. And it's asymmetric. It's ratcheting, right? So we go forward and come back when we reduce the load, but we don't necessarily always come back the same amount that we went forward. So the more we activate the slip band, the more we're softening and potentially destroying the structure inside.
Is the same as shear band?
It's different degree. Shear bands cross multiple grains. They tend to be more dramatic, right? So it's sort of a nomenclature thing, right? Where does a slip band end and the shear band start? It's kind of this. But in general, shear bands is more of a macro scale phenomenon, whereas slip bands are more of a granular phenomenon. right? Okay, so our particles can disappear by repeated cutting, right? Right. Essentially, if we keep shearing our particles, eventually they become small enough that they fall underneath our critical radius for a stable nuclei, and they just dissolve. Right? Gibbs-Thompson at work. Okay. Okay. So this is just an image here of a slip band in a grain. Right? You can see we've, through the repeated ratcheting, we've completely denuded the slip band, right, of any precipitates in there. So this band is now significantly softer than the surrounding neighborhood, which means that flow is just going to keep happening there, right? It's also becoming cold worked, right? So it's becoming more, it's losing toughness, right? Losing ductility. But even with that, it's still significantly softer than the surrounding area, right? So our strategy is we want to, strain localization is bad. So the strategy to improve fatigue resistance is we want to do anything that we can to try and delocalize slip. Okay? So some slightly larger particles rather than just the strengthening ones. The interesting thing is that impure alloys perform better than ones that are of high purity. Right? This is aerospace alloy 2024, right? Aluminum copper mag. The X designation is high purity. We see a marked decrease in the cycles to failure for a given cyclic stress amplitude. Right? As we make it more purity, right? So we nucleate these magnesium aluminum particles, right? Which means that we don't have a clear slip path, right? So we don't form slip bands. But we can't make these so large that they become easy to fracture, right? And destroy us the other way, right? If we make them too big, then we reduce our properties again. There's a sweet spot, right? We want to delocalize the slip, but we don't want to introduce other paths for fracture. Okay? So we can also go through thermomechanical treatments to increase our fatigue resistance, right? If we can get a really good fine dispersion in our solution heat treated, quenched, and aged alloys, right? Remember our the path that the dislocation took through our GP zones, right? Really fine particles. Right. So it's going through the notes, it's going to seem a little confusing, right? Because we sort of say big particles are bad, big particles are good. Small particles are bad, small particles are good. Right? It's all a matter of degree and subtlety and playing with things. Right? This alloy design is not easy. Right? And the same particle size in different aluminum alloys is going to give you a completely different response. Right? So the big message is we want to delocalize slip. We want to make our deformation as homogeneous as possible to prevent fatigue failures, right? But this is the same alloy, 7000 series, right? And we can see that operating in under different thermomechanical conditions can give us a big change in the fatigue resistance, right? That's sort of the big message here. right? This is not just a property of the composition, right? It also is strongly dependent on what we do to it, right? So for an example, of this, right? So we can see that the aluminum mag silver, right? The endurance limit is about 87 MPa, right? If we then age it, we reduce our endurance limit by almost a factor of 2, right? Because now we've made bigger particles that we can cut due to particle sharing, right? And then if we continue to age them, if we overage them, it goes back up, right? Because now we have big particles, right, that aren't going to localize the slip anymore, right? Now that we're going to loop around them, right? So it's all a matter of degrees here. Okay, and we will wrap there. I just have 2 more quick things. We lost a little bit of time because of the issues with the projector. So the last couple slides will hit Monday, and then through the week we're going to just go through the commercially relevant alloy systems, and wrap up aluminum alloys next week.